this is the most important problem on Swinburns test. A 10 kilowatts 250 volts DC shunt motor, a 10 kilowatts 250 volts DC shunt motor with an armature resistance of 0.8 ohms and field resistance of 275 ohms and takes 3.91 amperes when running light. Light means this is under no load condition at rated voltage and rated speed. What conclusions can you draw from the above data regarding machine losses? That is our question. And calculate the machine efficiency as a generator. So we can calculate the efficiency as a generator when delivering an output of 10 kilowatts at rated voltage and speed, and as a motor drawing an input of 10 kilowatts. So what assumption, if any, do you have to make in this computation? This is our question. So in the previous lecture we discussed the efficiency of a motor is calculated if you know the losses. Similarly, same way the efficiency of a generator is also calculated by using a no load test. So by using a Swinburns test we can calculate the efficiency of a generator also. Our supply voltage is 250 volts and the armature resistance is 0.8 ohms and the shunt field resistance is 275 ohms and I0 value is 3.91 amperes. 3.91 amperes. So ISH is equal to V divided by RSH. That should be equal to 250 divided by the RSH value is 275. That should be equal to 0.909 amperes. So if you draw the shunt motor diagram, so this is the shunt motor diagram and supply voltage which is given V, this is 250 volts. The current which is flowing through this is IA and this one is ISH. RSH is equal to 275 ohms. Under no load condition means, under no load condition, the I0 value, that is called the line current, you can say that IL0 or I0 is equal to 3.91 amperes. 3.91 amperes. So if you want to calculate the IA0 is equal to IL0 minus ISH. So approximately 3.91 minus 0.909. So it is approximately equal to 3 amperes. So first of all, calculate all the losses. No load armature copper loss. No load armature copper loss is equal to IA0 square into RA. 3 whole square into 0.8. That should be equal to 7.2 watts. And the no load input power is equal to V into I0 is 250 into I0 means IL0 only 3.91, that should be equal to 977.5 watts. So now the constant losses is equal to no load input power minus no load copper losses. No load input power minus no load copper losses. So 977.5 minus 7.2, that should be equal to 970.3. Once again, the input power is equal to constant losses plus copper loss only. That copper loss is also called as a variable loss. That too, this is no load copper loss. Then if you want to find out the constant losses, this is called the no load input power. The useful output power is 0. By using that formula, constant loss is equal to no load input power minus no load copper losses. The shunt field copper losses is equal to ISH square into RSH, then 0.9090 whole square into RSH is 275. That should be equal to 227.22 watts. That is about the shunt field copper losses. So we can find the stray losses. Stray losses is equal to, from the constant losses, if we subtract the shunt field copper loss, then I get the stray losses, shunt field copper loss. So that is 970.3 is the constant losses. Shunt field copper loss is 227.22, and finally I got it as 743 watts. B. When machine running as a generator, is first of all is asking a question, find out the losses. After that, when running as a generator, the output is 10 kilowatts, then VT into IL, terminal voltage into load current, is equal to 10 into 10 to the power of 3. The load current is equal to 10 into 10 to the power of 3 divided by the terminal voltage is 250 for a generator, so 40 amperes. The shunt current is fixed, that is 0.909 amperes. After that, you should calculate the IA value. 40 plus. Why? Because for a generator, IA is equal to IL plus ISH. 0.909 is 40.91 amperes approximately. Then input is equal to output power plus losses. The output power is 10,000 plus losses is 40.91 whole square into RA is 0.8 plus constant losses. What are the constant losses? Yes, it is a constant 970.3. Then I got the input power is equal to 12309.20 watts. So then calculate the percentage efficiency is equal to output power divided by input power into 100. So 10,000 divided by 12309.20 into 100. So that should be equal to 81.24%. The last question is, when the machine running as a motor, so we can calculate the same thing. IL is 40 amperes, but this IL is called the line current. The 10 kilowatt is input, that should be equal to supply voltage into line current. The supply voltage is 250 volts. Substitute here, then you will get the IL is 40 and the ISH is same 0.91 amperes or 0.909. Then calculate IA value, IL minus ISH, that should be equal to 39.09 amperes. Then find out the armature copper loss. This is also called as a variable losses also. IA square into RA is equal to 39.09 whole square into 0.8, 122.48 watts. What are the total losses? The total losses is equal to 122.48. The constant losses is same, that is 970.3. Then 2192.78 watts I will get. Then output is equal to input minus losses, 10,000 minus 2192.78, so 7807.22 watts. So motor efficiency is equal to output power divided by input power into 100. 7807.22 divided by the input power is 10,000 into 100. That should be equal to 78.07%. See, if you observe, for the same input, for the same power, that is the 10 kilowatts is the output power for a generator, the efficiency, see, the efficiency of generator is greater than the efficiency of motor. For same 10 kilowatts, 10 kilowatts is the output for generator, 10 kilowatts is the input for the motor. So this is the most important problem and a repeated problem in an examination.